Greetings, friends. In this little video, I want to talk about what can be a confusing topic. It's that of the Synergetics Constant, which I usually call S3. And I call it that based on this table. This is in the section of Synergetics where Bucky is explaining about his confusions regarding the T and the E modules, or the confusions which led to that discovery, which I chronicle in more detail in a video called Bucky's Subconscious Demon of April 1st. This is about S3, really, the Synergetics Constant to the third power, you might say. It's used for volume conversion. So I've compared it to American dollars versus Canadian dollars. Or I've talked about Martian math, because it's a little bit alien, this idea that there even could be a different model of what it means to multiply in either 2 or 3 dimensions, or in 4D, as we might say, in Synergetics. This is our standard way of doing a unit of volume as a cube, and let's call the edges R for now. That R is going to stand for the radius of a unit radius sphere, so it makes sense to say those are unit. And 1 times 1 times 1 is 1. So this is the Cartesian XYZ volume system that we're used to and that we all learn. Now what we have in Synergetics is a little bit different. We have D coming off from each corner of the regular tetrahedron, and D is 2R. So by convention, we say the Synergetics constant is the ratio between these, what it would take to express unit volume using these as units or using these as units. This would be the Synergetics picture of D to the third power. Now another way to look at that is with our unit cube. Actually, this is not a unit cube. This is our canonical cube of volume 3. So we wouldn't call this a unit cube. By the way, I'm pulling these out of a bag here. This is the bag, a souvenir bag I got at the first international conference on Buckminster Fullerene. I had the privilege of attending as a fellow of the Institute for Science, Engineering, and Public Policy, and that was in the 1980s sometime. I drove down to LA first and visited with the Buckminster Fuller Institute, then on La Cienega. In LA, they were going to move to Santa Barbara soon, but they hadn't yet. And then I moved back to Santa Barbara and went to this conference where the Nobel Prize winning discoverers of Buckminster Fullerene were all there. I got to meet Sir Harold Kroto, the late Sir Harold Kroto, who has had conversation with me since by email about the naming of Buckminster Fullerene, which is C60. Fullerenes is a whole family of carbon cage molecules. Buckminster Fullerene, most formally, is C60, one of those. Anyway, inside that bag I have this cube made of mites, which I take up in another video, the mite minimum space filling tetrahedron. And I always say these have volume 1/8 in Synergetics. They break up into 3 submodules or 3 smaller modules, A and B, 2 A's, 1 B, each the same volume, each a volume of 1/24. 3/24 is 1/8, and 24 of these fill this cube, create this cube, you could say. So this would have volume 3 for us, very logical. But if you stop to think about it, maybe not so logical, because these are the edges we call D, like in the picture above. And they're all coming off from the corner here, similar to the picture, as face diagonals. Those are our Ds, okay? Now, these are not going to be unit, even in XYZ. If we accept these as 2, let's say, relative to unit radius spheres, sphere here, 2 connecting the 2 centers, then let's say these are square root of 2, these edges. So the volume of this cube would be square root of 2 times square root of 2 times square root of 2, height, width, depth. So square root of 2 to the third power. However, we just went through why in synergetics we call this volume 3. So it's the ratio of 3 to square root of 2 to the third power that defines this S3 constant, which I've got here in the Python REPL. S3 is defined as the square root of 9/8, which is just another way of writing 3 over square root of 2 to the third power. Now there's another interesting fact about the S3 that I am checking out in this Python program. I've used this program already to look at the volume of the S module. However, on lines 28 through 36, I start out with the cube octahedron of volume 20, which I'm reaching for here. That would be, let's say this is our volume 20. Now remember, with the application of 1 over the S factor, the volume becomes 18.51 ... becomes the volume of this icosahedron. As we squish it down a bit, it torques, it rotates, and we get an icosahedron with the same edge lengths all around, 20 equilateral triangles. This is the volume 18.51. Now it has a dual. It has a dual, a pentagonal dodecahedron that we can make cross at the edges at 90 degrees, and that's going to be our rhombic tricontahedron, right? And at that size, when you're starting with the volume 20, going 18.51, and building that rhombic tricontahedron, we call that the super RT, because it's bigger than the RT we usually talk about, which is the one that precisely shrink wraps a unit radius sphere, in which case it's made of E modules, or it's exactly 5 in volume, which is very close to the E modules one, but a little bit smaller. I cover that in another video, RD versus RT, or vice versa. So the T and the E modules, that whole story. But right now we're just talking about the super RT, which is the bigger rhombic tricontahedron made from the 18.51 icosahedron and its dual. It turns out that, and this is something David Koski drilled into my thinking, I'm very grateful for that. It turns out that the synergetics constant, as I've been calling it, S3 times 20, or the cube octahedron's volume, gives us exactly that volume, the volume of that super RT, in tetravolumes, remember. All of this is in synergetics and in tetravolumes. Now there's another way to look at the synergetics constant, and that's as a ratio of two tetrahedra and their volumes. And this is going to connect back to the Martian math diagram at the end. So here we are in what we call the tetrabook. This is 3 equilateral triangles. The edges in red are all 2, or D. And it's like a book, a triangular book, open like this, with a page that goes back and forth. You could say wags back and forth. And in the position we're in right here, with the green edge the same as the red edges in terms of length, that's the synergetics volume of 1. Now if we rewind the tape a little bit to the vertical position, this is where the page is standing straight up, so we have equal tetrahedra. They're always going to be the same in volume, but here they're even the same in shape on both sides of the page, the blue edge and the green edge. This in synergetics units would have the volume 1.061, which is S3, the number we've been talking about. It's a little bit bigger, obviously. As the flap goes up towards the vertical, it's achieving a maximum volume at this point. Now, how that relates to the Martian math diagram is this upright cube with edges D, the red edges are D, not the green. It has the volume identical to that of the R-edged cube. So half the length, half the red edge is 1. And if you build a cube out of that, you're going to have the same area, or excuse me, the same volume as this particular tetrahedron. And that's the XYZ idea of a unit of volume. And we've just looked at the other tetrahedron, which is when all the edges are the same. And that's the Martian or the Synergetics version of the unit of volume. So again, going between them is what this chart is about, where Fuller is explaining the mistake that he made regarding what gets to be volume 5. He's on the brink of discovering the T and the E modules, and he's trying to recapitulate his thought process, what went on there. And he publishes this table, 986.209, and that's where S3, S to the third power, is the one we're looking at here. Now you can also call that the square root of 9/8. So that's a good review of how the Synergetics constant works. Let me run this program, by the way, because all I did is clear the results. What you're seeing here at the end are how the cube octahedron of 20 multiplied by 1 over the S factor gives the 18.51. And it's by creating the rhombic tricontahedron from that, we get the super RT, and a way to compute the super RT's volume, and this would hold true for any cube octahedron. If you jitterbug it and then create the RT out of the results, just multiply it by the Synergetics constant, i.e. 20 times S3, and you get this 21.21 of the super RT. Now we shrink the super RT down by phi, and that's what gives us the E modules RT, which we're more used to. The volume of the E and the S are given above, the E being 120th of that rhombic tricontahedron. And those E modules, their volumes, again, are just a little bit more than 1/24th. So when we actually shrink down to have the volume be exactly 5, that we get the T modules, and their volume is 1/24, same as A and B's. So check out the video on the A and B modules as well. And I hope this clears up some confusions perhaps about just what we're doing with this Synergetics constant. We're creating a way to go back and forth between alternative ways of modeling volume. Thanks a lot, and talk to you soon.